Okay, so I think we should be okay now. So we were talking last time about three-phase. I want to talk about three-phase in a kind of a practical sense here. I think I've got some handouts with this. Yeah, here we go. So most of your handouts, I think, are a single page with two sides. Some of them are single-sided that are stapled together. But as you saw last time, we have two systems. We have a delta system and a Y system. These are both used and both quite common. A couple of the most common variations of those would be a 208 system and then a 240 system. So we'll look at both of those. That's not to say that's the only three-phase system. If you start to look at heavy industrial power, the amplitudes are going to get quite a bit larger, but the arrangement, whether it's a Y or whether it's a delta, should remain the same. So the first one I'm looking at here is going to be a three-phase system that's a 4-wire, and it is a Y system. So I'm looking at this one right here. And if we were to look at that Y arrangement, we'd have voltages like that. So from the neutral, this would be the neutral here, from the neutral to any one of the lines. This is, let's say, the A line, then the B line, and the C line. From the neutral to any one of the lines, we have 120 volts. But then when we go from line to line, if I were to go from A to B, I have 208. If I were to go to C to A, I have 208, and so forth. And we'll see that relationship. How do you get from 120 to 208? We'll see that today. But I wanted you to have a practical sense of this. If you look at a three-phase panel like you might have in an industrial setting, this is not something, as I mentioned last time, that you're going to have in your house. But if you go to an industrial setting, I mean, if you want, we can take a tour of the electrical panels down in lab, and I can show you the difference. But this is showing you the layout of the panel, how you can get single-phase circuits and three-phase circuits out of the same panel. When you start pulling single-phase circuits out of them, you can begin to unbalance it. But if you pull 3 single-phase circuits out of it, you stand a chance of keeping it fairly balanced. So that's kind of a practical drawing there. The next picture, and that would be flipping over or turning the page in your handout, would be the delta system. This is probably a little more common. Okay, the 240 delta system. This is kind of nice. It's the neutral comes off the middle here, so that's the neutral. Then we'd have the A and the B and the C, and this indicates the wild phase. If you look at a panel and there's the wire, they use black for all the wires, and then oftentimes there's one that has some orange tape wrapped around it. That's going to be the wild leg, and that gives you a lot more combinations of voltage. So you can see from the neutral, we get 208 from the line to the neutral. From line to line, we get 240, and some of them we have 120. So we've got a very useful system there. And this is actually what it looks like if we look at it in a panel form. And usually, and you'll see this down in lab, we have one panel for 240 three-phase, and we have a whole other system for 208 three-phase. These are not something we're necessarily going to mix. So as we go through and talk about these, I just wanted you to have a sense about this. Questions with that? Okay. Well, so how did we get on that first Y? How did we get from 120 volts to 208 volts and whatnot? That's what I would like to address with this. And we could analyze this for a source if we wanted to. I'm going to analyze it as a load, so I come up with a Y load. So this is a Y. Okay, and I'm looking at a Y, so I've got impedance A, impedance B, and impedance C. And remember, we were going to make sure that everything was balanced as we go through this. And there's some voltage values here. I'm going to say that this is the voltage, let's say, at A with respect to B. So that's the voltage at line A with respect to line B. This is the voltage at line B with respect to C. And then this is the voltage here at C with respect to A. So those are what we call line voltages, line to line voltages. We're measuring the voltage from one line to another. These other voltages here, where I'm going from the neutral, this would be VAN, the voltage at line A with respect to the neutral, the voltage at line B with respect to the neutral, and the voltage at line C with respect to the neutral. And we call those phase voltages. What that is the voltage at the line with respect to the neutral. We call those the phase voltages. And we would expect the line voltages to differ from the phase voltages, and indeed they do. They differ not only by magnitude, but they also differ by angle. So I could talk about these. I think the one that I'm going to predominantly talk about is this one, but we could make the same argument. I could go through the same proof twice again, but I think I'll just go through this one at once, and I think it's a fairly easy extension. So let's look at this. If I talk about the voltage A with respect to B, so there's the voltage at line A with respect to B. That's this one right there. And I could say that that's really, by Kirchhoff's law, the voltage AN minus voltage BN, right? So, I mean, if you're at this point, if I travel this way, that would be minus BN plus AN would get me there. This is simply Kirchhoff's voltage law. Okay. So I'm going to write that, and I'm going to substitute into that the expression for voltage AN, which would be this, and the expression for voltage BN, which would be that. And you'll notice that I've taken the magnitudes the same. I'll just say it's V phi, some value. Okay? You could pick several thousand volts if you're one of those big industrial people. You could pick a lesser value if you wanted to work with a smaller system. Whatever magnitude you want, but it's the same. And then looking at this, if the A phase was 0, the B phase was minus 120, and the C phase was positive 120, have we picked a positive or a negative phase sequence? Positive sequence, right? That's a positive sequence. Okay. So with that, let me make that substitution. So I can say that voltage AB is equal to, what's AN? That's V phi at 0 degrees, and then I need to subtract off BN, which is V phi at minus 120 degrees. Is that right? And let's see, I can work with this. This is really V phi at 0 is just V phi, isn't it? And then I need to subtract off, I'm going to use Euler's equation for this. I'm going to say that this is V phi times the cosine of minus 120, and then I subtract, because that negative would get distributed through, J times V phi times the sine of minus 120, right? So that's Euler's equation. So if we work through that, we could say that this would be V phi minus a half V phi plus, is that going to be a positive? Let's see, I'd have a minus, oh, this should be positive because I'd have a negative, yeah. And then I'd have what, positive here. So positive J root 3 over 2 V phi, right? If I go to my unit circle and look at 120 degrees, I should come up with those values, remembering that I've got a negative there and a negative there. I think that's what I'll come up with. So I could say then that, let's see, this is really equal to, what's the magnitude going to be? I've got 3 halves, because 1 plus a half is 3 halves V phi plus J root 3 over 2 V phi, which I could write in magnitude angle form, right? I could say that this was equal to V phi times the square root of 3 halves squared, 1.5 squared, plus 3, root 3 squared is just going to be 3 and 2 squared is 4, at the angle of, what's the angle? The arctan of square root of 3 over 2 divided by 1.5, right? And when you go through this, this turns out to be equal to the v phi times the square root of 3 at an angle of 30 degrees. Now remember what we were looking for. We were trying to talk about VAB. So this is to say that our line voltage, which is line to line, is equal to the square root of 3 times the phase voltage which is our line to neutral, and then there's some phase shift in there. It's what, plus 30 degrees. Okay. So if you tell me what your phase voltage is, that your line to neutral, I multiply it by the square root of 3, that gives me the magnitude, and I shift the phase by 30 degrees. Now this 30 degrees definitely has to do with this being positive, this positive phase sequence. If it's negative phase sequence, I'm going to subtract 30. And I can sum that up when we get done with the delta. I'll try and sum that up in a conclusion.
Why did you start off with positive?
I started off with positive because I took this as negative. If you want to start off with negative phase sequence, that would be positive. Okay. So going back and thinking about the relationship in the y, and we had those two numbers. We had what? 208, and we had 120. What if you take 120 and you multiply it by the square root of 3? What do you get? 208. So that's why we see those numbers pop up. Okay. Now I could go back and do this for each one of these, but I don't think we need to. We know that it would be the square root of 3 each time. Usually the biggest thing people have trouble with the square root of 3 is they like to say square root of 2. Remember, square root of 2 is the conversion for your RMS on your sine or your cosine wave. Square root of 3 is our conversion for line voltage and phase voltage. Does that make sense? The line voltage should be more? I think that hopefully makes sense. Sometimes then it's hard to remember about this phase shift, and I'll try and summarize that. Well, before I put together that summary, this is going to happen again. Well, maybe I should look at the current here. If the current is easy in the Y, isn't it? This current here that would be in the line, is that the same as the current there that would be in the load? Yeah, that is. To try and say that those are different would be foolish. But when we start to look at the delta, things change on us. So again, we could do this for a source. We could do it for a load. I'm going to do it for a load, and this is our delta. Okay, that's our delta. And to talk about the phase voltage and the line voltage being different would be, of course, foolishness here. If I look at the voltage across here, that has to be the voltage line to line, doesn't it? If I look at the voltage across one individual load, I have 3 loads here, and presumably they're all the same impedance. The voltage across this impedance, that would have to be the voltage line to line. But it's the current that changes. I think you could imagine as this line current, I little a big A, goes to point A, it could split between these two branches. So we want to try and relate those. So let's see if we can do that. I could talk about relating I little a, big A, that's the line current. That's the line current. And relating it to the phase currents. What could I say this? I could say that this is IAB minus ICA. That's really just a statement of what? Kirchhoff's current law, isn't it? I'm doing Kirchhoff's current law at this point right here. I've got I little a big A going in, and that should be equal to I AB leaving, and ICA leaving, but ICA isn't leaving, so that's why I've picked up a negative sign. So now if I make my substitution, and just like in the voltage case, I set up my currents here. These are my phase currents. Okay, so I set up my phase currents with the same magnitudes, and I just shifted the angle by 120. And again, by this angle orientation, what do we have? Positive or negative phase sequence? Positive phase sequence, isn't it? Okay, positive phase sequence. So if I make the substitution, I could say that I little a big A was equal to IAB. What's that? That's going to be I phi at an angle of 0 minus then ICA, which is going to be I phi at an angle of 120. Very similar to the math we had on the previous page, our previous concern, right? I won't go through it in all the details, but if you go back through the math, really the only thing that's different is not having the negative sign there. And we'll say that I then little a big A is equal to the square root of 3 times I phi at an angle of minus 30 degrees. We picked up that negative because we didn't have the minus on that 120 like we did for the voltage. So we could do this again for the other ones, for IBB and for ICC. I don't think we need to because we can extend into that. More important is to spend some time on what does this really mean. Well, this means that the line voltage, not the line voltage, the line current, so that's the current going down the line there, is equal to the square root of 3 times the phase current. And then I have to shift this by minus 30 degrees. And again, this is due to a positive phase sequence. If someone gives us a negative phase sequence, we're going to have to be careful of that, and I'll try and summarize that pretty soon. Does that make sense? The line current should be greater than the phase currents. I think that's true. Hopefully that makes sense. This one is always a little harder. You have to try and remember which way you shift that. So the voltages are the same. The currents differ here. So let me try and put this together in some sort of a review. So we'll have some sort of a guide to three-phase. And we'll talk first about the Y. Okay, what do we get with the Y? If we back up and we look at this thing, when we were talking about the Y, we were talking about that the current is the same, but the voltage is different. That's where we were talking about line-to-line voltage, or what we call line voltage. We were talking about line-to-neutral voltage, or the phase voltage. So let's make a summary here. We can say that the line current and the phase current is the same. So the line current and the phase current is the same. And then what about the line voltage? The line voltage is equal to the square root of 3 times the phase voltage. Okay, where line is really line to line and phase is really line to neutral, right? This means I guess I should probably put voltage in there, shouldn't I? So the line voltage, that would be line to line. And the phase voltage, line to neutral. Okay. And we not very often do we say line to line. We'll just say line voltage. Everyone knows what we're talking about. Not very often will we say line to neutral. We'll just say phase voltage. Everyone's going to know what we're talking about. Now, what do I do if it is positive phase sequence or negative phase sequence? The best way that I can summarize this is just with an example. So let me say VAB is equal to the square root of 3 times V phi at plus 30, and that's a positive ABC. And we could say that VAB was equal to the square root of 3 times V phi, exactly the same magnitude, but here I have a minus 30 degrees, and what do you think that's for? Negative or ACB, right? So something like this on your formula card would probably be a good plan. Okay, so line current, same as phase current. The line voltage is equal to root 3 times the phase voltage. And then how do you deal with the phase shift? Remember that example. Well, let's talk about the delta then. So what were we talking about with the delta? Where's that one? Right over here. That was our delta where the voltage was the same, wasn't it? The line voltage and the phase voltage is the same. To say that the voltage across here is different than there is just nonsense. But it was the currents that were different. So let's address that. I guess I got an S in there when I need a G, don't I? Okay, so I've got the line voltage same as the phase voltage. And then I need to talk about the currents. I could say that the line current is going to be equal to the square root of 3 times the phase current. Okay. So the line current is greater than, multiply the phase current by the square root of 3, in fact, to get the line current. And an example of this, again, would be to say that I, little a, big A, is equal to the square root of 3 times I phi. And then I have to subtract off 30 degrees, and that was for what? The positive ABC. And conversely, if we went through the derivation, I mean, I'm not just making this up. I mean, if you look at this and you go back through this and you assign this as a positive number, so did I get that as a, oh, nope, I'm sorry. You'd have to assign this as a negative number, so this would be negative, and this would turn out to be positive. So you're going to say then that I, little a, big A, is equal to the square root of 3 times I phi at positive 30 degrees. And this is for a negative phase sequence, or ACB. Questions of that so far? So the first part of these is fairly easy to remember. It's usually easier to think that the line voltage is larger than the phase voltage, that the line current is larger than the phase current, and then you just have to flat memorize the, whether you're shifting at 30. I don't have a good, whether you're shifting at 30 or minus 30, I don't have a good way of trying to describe that. Now if we go back to our pictures from the beginning, what do we have here at the Y? What was this 208 here? That was line, wasn't it? Okay. And what was this 120, for instance, right here? That was phase. So if I take 120 and I multiply it by the square root of 3, do I get the 208? Yeah, in fact you do. Okay. So that's where that comes from, not some magic somewhere. Well, the other thing that we have to concern ourselves with is, and I mentioned, so I should probably say that this is more of the three-phase guide. So when we were trying to convert from a y to a delta, because remember when we had systems that we had maybe a y that was driving a delta, we were going to try and convert that to a y, right? Or if we had a delta that was driving a y, we were probably going to try and convert that to a y, right? So we want to be able to convert from a delta to a y, and this is really very much related like to those delta to y conversions that you saw last term, way back in the first class. Actually, the first few weeks of the first class. So if I were to take this, let's say, and I'll do it for a load. Sometimes you can do it for, you have to do it for a source if you have source impedance. But if I take this impedance in the delta, and I want to convert this to a y, like that. Each one of these would be my z sub y. I'll say this is typical. This would all be the same. Whereas each one of these would be z delta. Again, that's the same for all of those. Those are not the same. I can't just, like in a Rector set, take these apart and reassemble them there and have the same thing. That is not true at all. What you have to do, if you want a proof of this, is go through looking at your delta. Take this delta and then superimpose this y on top of it, and then start to look at the equivalent resistance between any 2 points, and you will conclude very quickly that your impedance for your y is equal to the impedance for the delta divided by 3. But remember back when they were all resistive, and you had those resistor values, if you go back and you make all the resistor values exactly the same, you will see this 1/3 with that. Okay, so there's nothing really new there. Well, that's a powerful tool when I want to try and convert my delta to a y. For instance, if you have an impedance here that's delta and you want to get it to a y, you just take those impedances, you divide it by 3. We can go the other way if we want to. It's probably more common to be dividing the deltas by 3 and trying to turn them into a y. But the biggest thing that I can tell you is it's not just a matter of taking whatever is in this box and putting it in that box. That's not true. Okay.
That's only if the impedance and the delta are all the same.
Well, they'd have. We're predicating on everything we're talking about as being balanced, so they would have to be the same. And you might say, well, are things delta? Or are loads hooked up as delta? Are they hooked up as y? The answer is yes. You can actually, like a heater, get a heater and it's shipped to you and they don't make the final connections, and they tell you how to make the final connections, whether you want to hook it up with a delta or whether you want to hook it up with a y, depending on what kind of rating you want it to have. Eventually, we're going to do some examples here as we get going, but we'll talk after we do some examples about power, and you'll see that the power is the same for the two systems. I mean, if it weren't, one would just become a footnote in history, right? By the very fact that they're both used nowadays, you would assume that they both have similar efficiencies. So that would be the guide, the pedestrian's guide to three-phase. When you have a Y, the currents are the same and the voltages differ by the square root of 3 and 30 degrees. When you have a delta, the voltages are the same, but the currents differ by root 3 and 30 degrees. And then as you're trying to convert from a delta to a Y, you're going to have this 1/3 ratio. Okay. Well, the problems we're going to tackle, I think I've got another handout for that. Looks like this. So let me pass out that handout. You want to hang on to this handout because we'll be going back and looking at these problems in terms of power and whatnot. So we'll be using these same problems for several days. Everyone get one? Okay, so there's nothing particularly special about these problems. We're just going to be seeing them again and again, so I just thought I'd document these so I don't have to keep writing them out. Get a little efficiency that way. So we're at page 7 now, aren't we? So the three-phase problems, there's a couple of them here. We'll start out with this first problem here. We're told that a three-phase positive Y-sequence connected generator, and incidentally, if you look at the three-phase problems in the textbook, if you look at the three-phase problems in homework, they're almost always expressed in a verbiage form like this. They don't have a diagram, so we have to go from this to a diagram. So we've got a three-phase positive Y connected generator. So we have a Y generator that is connected. Let's see, it's got the generator impedance. So this is Z sub generator. The initial internal phase voltage of the generator is 120 volts, so that's our source. The generator feeds a balanced three-phase Y. Well, it shouldn't surprise you. The first example, the easiest example, is a YY. Okay, so it's YY. This impedance here, that's Z for the load. And the line, this is Z for the line. Okay. So I'd like to do a variety of things. The first thing is probably get some sort of a diagram. In engineering, we almost always want a diagram. So I'll start out here. I'm going to draw the single-phase equivalent circuit. I could spend time drawing the YY, but we really only need 1/3 of it. So I'll look at the A phase, and we have a source there, don't we? Down to this neutral. And then I'm going to have some generator impedance. And then I'm going to have some line impedance. And then I'm going to have the load impedance. Okay, and these are connected together. So this is our source. This is our line. And this is our load. So what's our internal source? Is 120. What's this business? Take the A phase internal voltage of the generator as the reference phasor. What's that mean? Yeah, take this A, if we're going to say that this is A and this is A, that this is 0. Okay, so we'll just reference that to 0. Then the generator impedance was 0.2 plus J 0.5. The line impedance was 0.8 plus J 1.5. And what was the load? Should hopefully be the largest. 39 plus J 28, right? So is that appropriate single-phase equivalent circuit? Yeah, it is. Well, one of the things I might like to get is the current. I little a, big A. Could I get that? Yeah, that's pretty easy. I little a big A is going to be equal to 120 at 0 divided by the total impedance. What's the total impedance? Well, 0.2 and 0.8 is 1 and 39. That gives me 40 plus J. If I have 0.5 and 1.5, that gives me 2, and 28 is 30. So I'm going to have 40 plus J 30. Is that right? Anyone got an answer for that? I think we're going to have 2.4 at an angle of minus 36.87, and that's amps RMS. Anyone else get that? Okay, great. So from there, as we finish up for today, what would, and normally we won't even do this, we'll do this for a couple problems just to make sure that everyone's catching on, but usually if we write this, then we're probably good with it, but since we're just starting out, we need some practice. What's I little b big B, and then I little c big C? Same magnitude, right? 2.4, 2.4, and then is it positive or negative phase sequence? Positive phase sequence. You got to read this for everything it's got, right? Positive phase sequence. So what am I going to do? Subtract 120. So if I subtract 120 from this, so minus 120, lands us down here at minus 156.87. I have too many significant figures, but that's fine. And then over here, what am I going to do? I'm going to add 120. Where's that take me? 83.13. And again, those are amps RMS. Well, pretty soon, when we get together next time, I'll go through this again, just if anyone struggled with it. But we'll probably start to ask questions like, what is VAN? Or maybe over here, what is V capital A-N? And those will be pretty easy to get once we've got the current, right? Yes? Total? That's just the total impedance for the branch? So like I said, the tough part of this is not the math and the analysis. The tough part is what's meant by all these terms. When they ask for a phase voltage, when they ask for a line voltage, what are they really wanting? And we'll practice that as we go through these. Take care till then.